All right. Hello, we are the Niceday group, and our project sought to eliminate bias in skin disease detection. So our project was inspired on the issue of when given images of dermatological diseases, certain skin types are harder to diagnose than others. Based on the article from MIT News, from a group of 1,000 dermatologists, they were only able to accurately determine around 38% of images with skin disease, and only 12.9% of darker skin images were correctly classified. And our goal was to train an ML model using transfer learning to correctly classify diseases, no matter the disease type or skin color. So our data set was a subset of the full Fitzpatrick set that had around 17,000 images and over 100 plus types of conditions. But our set was only 4,500 images of 21 dermatological conditions with different skin tones. And some of the important data from that data set was the skin tone, the diagnosis, the diagnostic categories, and the quality control check. Some of the problems with this data set, however, was that the set was clearly pretty small, and it also lacked data for darker skin tones, and also skewed distribution of disease types. To fix this, we used data processing by augmenting the data, which was done by rotating or flipping images, to increase data for underrepresented categories, and we also used data resampling. So these graphs here further show the uneven distribution of diagnostic categories for different skin tones with a clear bias towards lighter skin tones. And this is why the data pre-processing was a very important part of our project. Our main tools used were Python for data pre-processing, Pandas data frames, TensorFlow for the model, and Jupyter Notebook.
One of the big challenges in our project was that there wasn't enough data to train the model on, especially with one of the skin disease categories. So to do with that, we used data augmentation, like the image on the right shows, by using this like rescaling, flipping, blurring, and more to generate more data to train the model on. We also tried fine-tuning training parameters, like changing the weight loss functions parameters, as well as setting schedules for learning rate and unfreezing layers so the model training accuracy wouldn't plateau. The strategy we applied was data resampling. We oversampled the minority class to make the overall distribution look more equal. On the right, there's an image of what our data looked like initially, and then after oversampling, all the disease skin type categories look a lot more equal. We also took a transfer learning approach to train our models. So we tested various pre-trained models to see which one worked the best, like efficient net, resnet, and convolutional next small, to see which one worked best with the type of data we had.
Next, let's talk about our model architecture. We settled on the convex small model because our data is relatively small, and this model is commonly used in image classification tasks, especially in the medical field. The first layer is used to get basic features like the edges. The middle layer has additional filters to pick out more details, as well as an activation function to add flexibility. And the final layers, they summarize everything into a smaller feature map. Then it picks out the most important features of the image and makes a prediction about the type of the skin disease. So our end result, we trained our model on 4,500-ish images of various skin diseases. And after trying out a bunch of model, we settled on a convex small model, and that yielded a validation accuracy of 60.9%. We kept the epochs low due to time constraints, but maybe we could achieve better results with more epochs.
In the end, what we learned was because of the low amount of time we had for the hackathon, what we needed to do was do a lot of iterations. And basically, well, like we said earlier, transfer learning was an extremely important factor. Essentially, switching from different models was what ended up saving us the most amount of time and also improved the most amount of accuracy. In addition to this, it was important that we use a form of early stopping to prevent things like the program running for too many epochs, but then the val loss wasn't changing at all, which means our program wasn't learning. And when we added that, and then that was what we would use alongside scheduling, where we would lower the learning rate and it basically additionally train the model with more and more layers as time passed to prevent any sort of val log stagnation. And then after this, what we want to do for the future is use the F1 formula, which actually tests for the complete accuracy and not like a more local accuracy. And with enough training and a satisfactory F1 score, we could potentially export the model and for further uses to like maybe an app or something. Thank you. Yeah. Is there anything else we want to add? I'll just crop out and put in between.
It's like a little bit over. It was like 5 minutes, 11 seconds.
Oh, shoot. 5 minutes, 11 seconds?
Yeah.
You could just speed it up with like iMovie. Should I do it like
Yeah, we could
1.1?
like just cut down the seconds like when we're switching, and we could probably bring it down to 5. or do you want us to run through it again? Up to you.
No. Yeah, we can just speed it up a bit. Yeah.
Okay, perfect.